と難に負けそうな時、私が一緒に立ち向かってあげましょう。ごきげんよう。あ、こっちの言葉の方がより自然かもです。はじめまして。
Equal because they each have one hydrogen ion. So they have the lowest number of hydrogen ions, which means they have the highest pH. So you got to remember that kind of inverse relationship. More H plus or concentration is lower in pH. All right, last one on this set of representations. So now, which solution would require the largest number of moles of sodium hydroxide, a common strong base, to neutralize it? And which would require the smallest number of moles? So to neutralize an acid completely, a base reacts with every acid particle present in the solution, regardless of whether it's weak or strong. And so to determine this, we just need to figure out which solution is the most concentrated in terms of acid, and that one will require the most sodium hydroxide to neutralize it. And the least concentrated solution, therefore, will require the least sodium hydroxide. So looking at our representations, we can see that representation 4 has the largest concentration, so it's going to require the largest number of moles. And representation 3 has the smallest concentration, the fewest acid molecules, looks like 3 acid molecules in that solution. So that's how we would rank it. Oh, I'm sorry, we have one more on this. There's so many things you can do with particle diagrams. So this time, though, we're just going to focus on representation 4. And representation 4, we're going to try to calculate Ka. So let's look at the question here. Assume that each particle represents a concentration of 0.01 molar. Estimate the value of Ka for the acid in representation 4. So we've got to write the Ka expression, so that's an important thing to remember. And when we do that, we see that we have the ions, that the products of the acid dissociation in the numerator, and then we have the acid concentration, Ha, in the denominator. That's our unionized acid. So we need to count. We've got 16 Ha molecules, 1 A minus ion or conjugate base, and 1 H plus ion. And each one of those represents 0.01 molar. So then we can plug in our values to the Ka expression and calculate a value of Ka from this particle diagram. So these representations, particle diagrams, you will see them on the exam. I don't know if you'll see them in the acid-base context, but it's really important to be able to interpret them. So let's look at another type of representation that you're going to see a lot on acid and base questions, titration curves. So pH is on the y-axis and volume of titrant added is going to be on the x-axis. And here we have 3 different curves for 3 different weak acids. And the prompt tells us that the graph shows titration curves for equal volume samples of 3 different acids. And each sample was titrated with a 0.10 molar sodium hydroxide solution. So they're equal volumes of acid, and they were titrated with the same base solution. So that's helpful information to allow us to compare these acids based on this titration curve. All right, so rank the acids from most concentrated to least concentrated. So in order to talk about the concentration of an analyte solution in a titration, you got to know what the equivalence point volume is. And so the equivalence point is the middle of the vertical part of the curve. And in this particular graph, we can see that all 3 acids have the same equivalence point volume. It's at 25 milliliters. And all 3 acids were equal in in volume, and they were titrated with a sodium hydroxide solution of equal concentration. So therefore, given that they have the same equivalence point volume, they've got to be equally concentrated, these acids. We could calculate it, but that's not what we were asked to do here. We don't need to calculate the acid concentration to know that they have equal concentration. because of the situation that we were in. Okay, so now let's take this same graph and rank the acids from strongest to weakest. So which of these three acids is the strongest? Well, we need to focus on the initial pH. So the pH before the titration started, before any base was added. And the initial pH, of course, is at 0 milliliters, so at the y-intercept on this graph. So HF is about 2.2, KHP about 3.4, HOCl is the highest initial pH at 4.3. So the acid that has the lowest initial pH is the strongest, because we can say that with confidence because we know that all three of them are equally concentrated. And if they're all equally concentrated, then lower pH means that the acid has a greater H3O plus concentration, right? And greater H3O plus concentration implies that it has ionized to a greater degree, which is what we mean when we say how strong is the acid. To what degree does it ionize at a given concentration? So therefore, we can say that HF is the strongest of these three weak acids, followed by KHP, followed by HOCl by ranking their initial pH.